Hello everyone, my name is Miguel Jiménez and I work for the JavaScript Foundation team for Facebook London. And I'm going to be talking to you today about scaling JavaScript build systems. And more specifically, I'm going to be talking about Metro. So the first thing I would like to do is to show you a video about what the development process of React Native is. For those who don't know what React Native is, it is a framework built by Facebook that allows you to use JavaScript in order to create hybrid mobile applications. And it uses React as well in order to represent the layout. So this is the typical development process. You change things into your editor. We have the iOS and the Android emulator picking the change almost immediately. You can change text, but you can also change layouts. You can change colors. Both emulators will reflect your changes almost immediately. And the piece of infrastructure that it's powering all of these interactions is actually Metro. So to define it in a more formal way, we can say that Metro is the development platform for React Native. And it does that by exposing an HTTP server, so clients, in that case emulators, can communicate with it. And it also exposes a WebSocket server, so it can push updates into the clients. The main goal is to build JavaScript, but it can also do many other stuff. It deals with your assets, so when you want to add a photo or a video, Metro is as well in charge of bundling and adding this. It provides hot module reloading, and to some extent is also extensible, because the main interface we expose is a function that matches with Node's callback. So you can use that either on your Node project or on an Express app. And last but not least, it is also used in the building process. So once you've got your app ready and you want to ship that to the stores, part of the building process that will happen in your editor, whether if it's Xcode for iOS or Android Studio for Android, the process of taking all the JavaScript of your application and putting that inside will be done by Metro. So based on what we just explained, it looks like there are a lot of other alternatives in the open source world that pretty much fulfilled all of these goals. So why is Facebook building Metro? There are a couple of reasons for that. The first one is we wanted to make it fast. And by fast, I mean really fast. Our scale currently is at the tenths of thousands of JavaScript modules, and we're aiming to be able to perform reloads on a sub-second basis. So dealing with such a large amount of code in so small time requires you to have a specific setup that we'll discuss in a minute. The second thing is wanted to be scalable. You're probably aware that JavaScript is kind of a trending language. You can see that based on the audience. So the amount of files that we have at Facebook just keeps growing. It has to work not only for today's requirements, for these tens of thousands of JavaScript modules, but it also has to work for tomorrow. And the last and the third reason is we want it to be integrated. So Metro ships, when you are developing with React Native, Metro ships a set of really cool features that are deeply integrated into the bundling system. And my preferred one to explain this is the ability of reloading your React Native applications by using the shortcut of Command R or RR for Android. The way it works is Metro brings up a global hotkey listener. This gets inside Metro and it pushes an update towards the emulator so they know they have to reload. This, for developers that are used most to the web, it gives them a very seamless experience. And in order to achieve this, you also need to have very specific control on what your bundler is doing. And last, there is also a little bit of history. React Native was a project that was started 5 years ago, and back then there weren't that many open source solutions. So the first iteration for Metro was something called JS App Server, which then turned out to be the React Native packager, and about 1.5 years ago we extracted it into its own repository, which is what Metro is today. Okay, so now that we know what Metro is doing and why are we building it, I would like to get a little bit into the technical details of it. And we're going to do that by covering all the different processes that are involved in creating a bundle, from the point where you have your code up until you get your app shipped into the app stores and executed by your customers. So the first part is about monitoring the files on a project. As we said, we have quite a large code base at Facebook, and dealing with such amount of files can be slow. Imagine that every single time that you change a file, you need to retraverse your whole dependency graph. If we're talking about big code bases, this can take quite a lot of time. So the way it works inside Metro is by using a module from a friend project, which is Jest. In particular, we use Jest HazeMap. So Jest HazeMap, one of the features it has is that it has the ability of monitoring your file system and emitting changes every time it detects something on your file system. Now, in order to achieve this, it uses Watchman whenever possible. Watchman is another open source project from Facebook which monitors your file system, but as a daemon process. The cool thing about doing so is that if Metro gets killed and then you restart it, you don't have to recrawl the whole file system again. You can just query Watchman and tell Watchman, hey, can you give me the changes that happened since the last time I was alive, which dramatically reduces the startup time. However, on pretty much like all open source projects and general development, people does not have Watchman installed. So if we don't detect Watchman on the file system, we just fall back to fs.watch. This has a startup cost overhead, but after that, they're pretty much the same. So now that we know all the files that are going to get into our project, the next thing that we have to do is transform them. And in that aspect, Metro does what any other single bundler do, which is we use Babel. The thing that it's a bit different in Metro compared to other bundling systems is the way we execute Metro. So transpilation is a very expensive process, and it can take a lot of time. So most bundlers will have their main process, and they will execute the transpilation process one file after the other. You take A, transpile A, when you're finished, you take B, and so on and so forth. If you have, once again, a very large code base, this can take actually minutes to happen. So Metro uses a different approach. Instead, the main process doesn't transform any file, but it spawns a set of child processes that we call workers. Files are then sent in parallel to each of these workers. The transpilation happens at the same time, and then we return the result back. Now, we spawn approximately one worker per core, which means a time reduction of 6 to 7x on a MacBook with 8 cores. So this can cut down building times from minutes to seconds, which is pretty good. Now, parallelizing the process of transpilation poses a new set of problems. Imagine that worker number one is dealing with a very complex file, and it turns out that you change again a.js. Well, the naive approach would be taking A and sending it to the first available worker, which turns out to be worker number 2. Now, part of the transpilation process, they tend to have caches, intermediate caches, to make further transpilations faster. If you remember from the previous slide, A was transformed by worker number 1, so we set the cache on worker number 1. If you now send A.js to worker number 2, you're going to end up with the same cache on worker number 2. And this is pretty bad both in terms of space and time. It is bad in terms of space because memory between workers is not shared, so you're going to duplicate the same data structure. And it is bad in terms of time because since you didn't have any cache, you will have to retranspile from scratch. Instead, what Metro does is it implements a queue for every single worker. So the first time you transpile a file, it will be sent to the first available worker, but once it gets returned, the file will get stick to the worker that transformed it. Now, if you want to retransform it, we will put it into the queue, in that case of worker number 1, and we will wait for the file to finish in order to send A into the right worker. The overall process right now here is an oversimplification because it looks like worker number 2 and worker number 3 are idling, and we could just have taken that one. In real life, what happens is that worker number 2 and worker number 3, they're also busy with their own set of files. So it is not that we just have one worker super busy and the rest idling, but the load is actually distributed across all of them. Now, the module that powers this, once again, borrowed from another project, is Just Worker, which has a very simple API to create these kind of farms of workers. We have an example on the repository about parallelizing leftpath, which is not very interesting from the practical point of view, but it shows how easy you can do things. Cool, so we've transformed our files, and with the parallelization, it becomes pretty fast. But we still want to be faster than this. And in order to achieve this, Metro ships with an internal cache. This cache is a multi-layer cache, and it is located inside the main process. Now, the way it works is you go into the first cache layer. If the result is there, you will return it. And if not, you will go into the second cache layer, and you will repeat the process through all your layers. Every time you want to transform something inside Metro, you will go through a function called transform. And this transform will call into the caching layers. Now, the first one that we have is a local cache. This cache lives inside your laptop on the TMP folder, and it's used both in open source and internally at Facebook. Now, it could be that the thing that you're looking for is not on that cache because, for instance, you just checked out a new version of the code, and you've never seen that file, so it was never transpiled. So for that, we have a second cache layer, which is a centralized database. That one is only available at Facebook, but the code is open source, so you could, in theory, use that as well. And this centralized cache is accessed by all developers. Now we go into the cache and we look for the file. Could be that the file is not there as well because it has a local change that you've just done. In that case, the only thing that we can do is go into JS worker and transpile the file. Once the file is transpiled, we put that into the local cache, but we don't write to the global cache. And the reason for that is that if we save every change that every developer is doing through the day, we're going to end up bloating the cache, and there is no benefit for that because no other person will make the same modification over the same file and in approximately the same commit. Instead, at Facebook, the centralized cache is fulfilled by a continuous integration job that runs on master. And every time we see a new file, we just transpile the file, or a modified file, we transpile the file and we store it. Now, in order to store something, you need a cache key and a value. The cache key is built by Metro by combining two parts. We take your source file and we hash it, but we also take every single part that is involved into the process of transpiling the file, and we also hash it. And the result, the cache key we use, is the union of both. The cool thing about this is that whether if you change the file itself or you change the way you transpile, you don't have to worry about invalidating the cache. So if you didn't have the second part and you changed the way you transform, either you had to invalidate the whole cache, which can suck for people that it's not yet onto that commit, or you would be serving stale results for some times, which is not good either. So that was for the key. For the value is the result of the transpilation process. So if we take this module, for instance, and we transpile it, it would end up looking something like this. So const got converted into var, it got wrapped into a function, and we got the defined call, etc. Now, inside Metro, we do not use string identifiers for modules. Instead, we use numeric identifiers. Other bundling systems like Webpack and Browserify can do that through a plugin, but in the case of Metro, this is built inside the core of it. The reason is for performance reasons. It's always faster to do a lookup through a number, and for size reasons. A number is always smaller than a string. Now, if you cache this, you're going to have some issues because these numbers are local to your build. So while this could work for your local cache, for the centralized cache, when someone else is going to pick that module, their build will crash because left pad could be a complete different module than number 42. So Metro does not really hard code numbers. It adds one level of indirection by using an array of numbers. And each of the modules is changed, each of the reference of the modules is changed into a position into this array. Now, side to the module, we also store that position number 0 is left pad and position number 1 is 5. And when you build, we make a lookup into the table, we extract which is your local number for these modules, and we add this array to the define call. Okay, so we've got all the files transpiled, and we're ready to produce a bundle. Metro produces bundles through something that we call serializers, where you receive the graph and you can manipulate it in any way you want. Now, there are two default serializers shipped with Metro. The first one is a plain JavaScript bundle, and this is when you're developing in React Native in open source, it's the one that you're most likely using. It produces the same format that any other bundling system. We just take all the modules one after the other, we concatenate them, and at the end we add a startup code. The startup code is 99% of the times requires 0 because we assign numbers in DFS look-like when we traverse the graph, and your entry point will almost always be the first module. Now, there is a second format which is called random access module bundles. And this is not a text file, but a binary file. This file is composed by 3 sections. The first one is a magic number. This magic number will help us identify when we try loading it that we're not loading a text file, so plain JavaScript bundle, but a RAM bundle. It stands for FB0 bundles or something like that, the code. Now, after that, we've got a table of contents. The table of contents has the amount of modules that are shipped into this big blob. The startup length, remember the startup code was this require 0, and references to where each of the module is located into this gigantic blob. And after that, we just write the code, starting with the startup section and each of the modules, and we put after them a null character, and I'll explain to you in a second why we do that. Now, the amount of modules let us know how big the table of content is. The startup length is how big the initial length is, and each of the offsets are pointing to the first byte where the module is located within the file. So the format might look a little bit cumbersome, but thanks to the table of content, we can access any module in constant time. With very simple maths, we can get where it is located. And this is especially relevant to execute code on devices. This is very specific to React Native as well, and it's a little bit tricky, so I'm going to explain you first how we execute, how we require modules that were previously required, and then we'll take a look at how we load a module for the first time. So when the module was previously required, you will have into memory your require implementation and all the files, all the modules that were previously loaded. Now, when you want to require something, you will call into the require implementation, and the require implementation has its own internal cache. For instance, because requiring twice the same module has to return the same instance, it will query the cache, and then since the module is there, it will just return it. Now, this is a pretty straightforward process, and again, literally every single bundling system does the same. Now, when you require something that was never required, the process gets a little bit trickier. We have, once again, require and the modules that were previously loaded, and our require call to something that we've never seen. The process starts in the same way. We go into require, we make a lookup into the cache, and then 622 in this case is not there. So we got to load it. And this happens with a little trick. For loading 622, in the case of React Native, we do not use JavaScript, we use the native side. The native side has a function called native require, which require will call, and will tell, hey, can you please load 622 inside the JavaScript virtual machine? Now, native require will go into the disk, look at this gigantic blob, do the maths, take the first byte of 622, will extract where it is located, and will inject it inside the virtual machine. Now, this is the reason why there is a null byte at the end of every single module. Because all implementations of JavaScript virtual machines are C++ based, or at least they use ASCII-Z strings. By putting a null character at the end of each module, we don't have to worry neither about the length of it, nor copying it into a separate buffer. We can directly tell the virtual machine to just load the JavaScript from there. Now, once the module is loaded inside the virtual machine, it will self-register inside the require implementation, and it will appear into the cache. And the only thing that it's left is release the native require, and now require will be able to return that module. This process, pretty much like the RAM format, looks a little bit cumbersome, but it has some benefits. You have to pay off every single time that you cross from the JavaScript side into the native side, but on the other side, you're only loading the minimum amount of JavaScript that you need, and you're not consuming as much memory as you would consume otherwise. Loading a plain JavaScript bundle will still be possible, but it will take a lot of time and a lot of memory, and not all devices are capable to handle this. So by doing this, you're only putting inside the code that you, inside the virtual machine, the code that you really need to execute. So, we've talked a lot about how we bundle code, how we execute code, a lot of the building process. But what happens with developers? Because we said that we were looking for sub-second reloads for our developers. So how have we made this work internally? A couple of months ago, approximately 4 months ago, we developed something that is called the Delta Bundler. And this is also open source, and it is part of Metro. So in order to figure that out how it works, let's take this graph as an example, where your entry point is module number 1, and the arrows mean the first one is requiring the second one. So module number 1 requires the second one and the sixth one. Number 2 requires 3 and 4, and so on and so forth. The first time you want to load this inside the device, you will take all the files, put them all together, and send that to the device. Now, if you change module number 6, what most bundlers do is they will retraverse from number 1, get all the dependencies, create a new entire bundle, and ship that into the client. But the truth is, out of the 6 module, only number 6 changed. So what the Delta Bundler does is it creates a delta just with that module and sends that into the client. Now the difference is massive because instead of having an ON operation, every time you reload, you've converted the operation in an O1. It doesn't really matter how big your code base is. Once it is loaded for the first time on the device, you don't have to worry about sending everything over and over through the network. The process works like this for most of the changes. There are slight modifications when you add or remove a require. So when you add a require, we have to extract that require and start crawling again from that require. And through the crawling process, we only extract the modules that is the first time we visit. So for instance, module number 1 required number 7, and number 7 requires 4, 8, and 9 to work. However, we know that 4 was early loaded into the virtual machine, so your resulting diff will only contain module 1, 7, 8, and 9. In a similar fashion, when we remove a require, we have to verify that this was the last require going to the file. In that case, module number 3 stopped requiring module number 5, but module number 4 still depends on it. What it means is that the delta that we can send is only module number 3. Now, if we also change module number 4 and we remove the require, 5 becomes an orphan module, so we can safely delete it. And the resulting delta for this is patching module number 4, but also deleting module number 5. So to summarize this, most code changes only require patching a single file. So we've gone through having to create a gigantic bundle with megabytes and megabytes of JavaScript into sending just a few kilobytes. Now, when you add a require, we just trigger a depth search through all the new requires that we might visit, and we take only the ones that is the first time we see. On the other side, removing a require does the inverse operation. So instead of depending on direct dependencies, we depend on what we call inverse dependencies. So we look at who's depending on a module in order to know if we can safely delete it or not. If no one's depending on the module, you can safely delete it. Now, as a quick recap, we can say that Metro is a building platform where the scaling issues are put on every single part of the process. So we make transpilations in parallel. We have multi-cache systems in order to avoid having to retranspile files that someone else transpiled before. And then we have the code execution in the most optimal way, both in development and in production. So, if you want to try Metro, if you're developing a React Native application, you're already trying it. You don't have to do anything. All the features I've described are part, except for the global cache, because we cannot ship the global public cache. All the features I've described are in there. And we're also working into making it suitable for other platforms. So there are really cool examples about this. This is a video of a React Native application working on a browser. The thing that is powering this, I would totally recommend you to check the video. This is just 5 seconds. This is also powered by Metro. And in fact, we're currently working in making Metro suitable as well for web. And for that, we have a very simple application that a colleague of my team made. So you can just go and download it. Everything works on that app except for the Delta bundler. We're still figuring out how we're going to implement this on the web. Might be service workers, but this is definitely not there yet. But in any case, it's actually powered by Metro. And that was all for today. Thank you very much.